Okay, 16.4 gives you an introduction to changing a line integral back to a double integral over a region D. This is called Green's theorem. And you're taking the line integral of C over C of p dx plus q dy, and they're changing it into a double integral where you take the partial of q with respect to x minus the partial of p with respect to y. But there's a catch, because C has got to be a certain type of curve. It has got to be a positively oriented, piecewise, smooth, simple, closed curve in a plane. It's a handful of words. And D is just what's enclosed by C. P and Q have to have continuous partial derivatives on that region. So just going to go to right there right now. And I'll try to explain to you what a positively oriented, piecewise, smooth, simple, closed curve is. As soon as you get all that written down.
So we'll be testing the curves?
Do what?
We'll be testing the curves in order to use the curves?
Yes. You'll have to know whether it's positively oriented and whether it's basically closed is what you need to know. And those are the basic things I'll hit with y'all. Because if it's not positively oriented, it's not simple, closed curve, you can't do this. Which is the same thing with the conservative vector field. Those of you that are finished, I will let you go ahead and write this down. All right, this integral with a symbol, a little circle in it, I think y'all have used that in physics. You probably didn't know what it meant. Did it? Okay. It means a line integral is calculated with a positive orientation on your curve, which meant your curve's got to be going a certain direction. So that's the integral symbol with a little circle on it. So you have seen it before. I thought you had. And this is just the way to do the vector function using Green's theorem, using the positive orientation. I'm just curious, when you use this in physics, does it mean you have to go around your curve in a certain direction? Or have y'all ever paid attention to that?
I don't see.
No, it didn't really say?
Yeah.
Okay. Okay.
I mean, we're familiar with some of my friends, but he presented really didn't know he
Okay. Okay. When you see this symbol, it's supposed to mean that you're going over your curve C in a counterclockwise direction. It's got to be a counterclockwise direction. So your curve C is going to be going, doesn't matter if it squiggles around or whatever, but it needs to be going that direction to be positively oriented. So this would be C. This is a simple curve. It's closed. Closed means that the beginning point and ending point are the same place. It's closed, okay? It's a closed surface. And the region that it encloses is D. So you're going to change this integral over the curve C to a double integral over D, which is inside that circle, or not circle, but inside that surface D. C, I'm sorry, inside C. Okay. If your orientation is backwards, if your curve is clockwise, then all you do is stick a negative sign in front of your integral to change the direction. So if your curve is clockwise, then you put a negative sign in front of your integral, and that reverses your order, reverses it back the correct direction. Okay, so that kind of makes sense? Okay, it should. All right, so is there a question about this positively oriented? That's counterclockwise. Piecewise smooth just means it's relatively smooth. You know, it can be like that, or it could be this and then something like that. That's piecewise smooth. It's smooth on this piece and it's smooth on this piece. It's closed because the ending point and the beginning point are the same place. And it's simple because the curve does not cross itself. If the curve crosses itself, that is not a simple curve. It can't cross itself. Okay? So now let's look at some examples of how you can use Green's theorem to evaluate integrals. If you looked at problem 2, I'm sorry. Yes.
Okay.
Yes. It's simple, and it's closed. All right, line integral of xy dx plus x squared dy, and C is the curve with the rectangle with the vertices 0, 0, 3, 0, 3, 1, and 0, 1. All right, in this is the P, this is the Q, okay? Now we need to look at our curve, and this means we need the positive orientation, so we're going from the point 0, 0 to 3, 0 to 3, 1 to 0, 1 and back. So here is our rectangle. That's where our line integral is. Now, if we did not recognize that this was a simple closed curve with a negative, this has got a counterclockwise direction, because you look at the order they give you the points. 0, 0, 3, 0, 3, 1, 0, 1, you're going in a counterclockwise direction. So it is a positive orientation. So if you recognize that, and you recognize that it's closed, you can evaluate this integral by switching it to a double integral. So to do that, you take the partial of p with respect to y, which is going to give you x. You take the partial of q with respect to x, which is 2x, and you change this to a double integral over the region D of 2x minus x dA. Partial with q with respect to x minus the partial of p with respect to x. So this is the double integral. 2x minus x is x dA. So now you have to figure out your limits of integration for this, for your x's and your y's. These are all constants. So in my picture here, I've got x is going from 0 to 3, y is going from 0 to 1. So this changes to the integral 0 to 1, 0 to 3, x dx dy. And just evaluate that, and that is the value of this line integral. And I don't know what it is, but we can figure it out if y'all want. I believe I got 9/2. But y'all better check me. Know what you got? Okay. All right. Question about that one? Remember, you got to check for that positive orientation. You got to make sure it's closed also. Yes. Yes, I can think of a problem that we had back in when we first did line integrals, where the region was like part of a curve and then a line segment or something like that. that is not a simple closed curve because it doesn't come around and close itself up. So you could not use this on a curve that does like this because it's not closed, okay? So you need to look at your picture, make sure the points are given to you in the correct order to be counterclockwise and all that, okay? All right, let's look at another one. Let's look at, I don't know, let's look at number 5. Use Green's theorem to evaluate this. C is xy squared dx plus 2x squared y dy. And this time C is a triangle with the vertices 0, 0, 2, 2, and 2, 4. All right, so sketch your curve, sketch your triangle, 0, 0, 2, 2, and 2, 4, and then back to 0, 0. Now remember, ordinarily, if you didn't recognize this as Green's theorem, you would have to find a parametric equation for this line, this line, this line, and do 3 separate integrals and add them together. But this is closed, comes back to the starting point, so you've got the region, and the way they gave the ordered pair, 0, 0 to 2, 2 to 2, 4, and back, that is the positive orientation. So it's got the correct thing. It's got everything we need. So now we just need to do the P and the Q. So the partial of P with respect to Y is 2xy. The partial of Q with respect to X is 4xy. So we are changing this to the double integral over the region D. 4xy minus 2xy dA. Okay, so this is the double integral, oops, of 2xy dA. So we need our limits of integration for this shape back to 2 dimensions, so we need values for x and y. I would probably let my variable go this way, so I need to find the equations of these lines. This line has got an equation. It's going through y-intercept is z, 0, rise over run, 2 over 2. So y is equal to x. And this one, y is equal to 1, 2, 3, 4 over 2. Y is equal to 2x. So I would let my y's go from x to 2x, and my x's then are going from 0 to 2. So this is from 0 to 2, from x to 2x, 2xy, dy, dx. And so we change this line integral to this double integral, which is much easier than finding all of those parametric equations and adding them together. So let's see. Uh, 12? You make it 12? Maybe? Oh, if one of y'all tells me I made a mistake, I'm just going to say it's 12. I can't see a mistake. Did you get 12? Okay. Okay, and then let's do one like number 12. Is there a question on this one? All right, let's do a question like one like number 12 because it's set up a little bit differently. They want us to use Green's theorem, and they're telling us to find f dot dr, and they're giving us our f of x function. Your vector function is e to the negative x plus y squared, and e to the negative y plus x squared, and c consists of the arc of the curve y is equal to the cosine of x that goes from the point negative pi over 2, 0 to positive pi over 2, 0, and then the line segment from pi over 2, 0 to negative pi over 2, 0. Okay, first order of business, after we get it written down, is to draw our picture. Now, these coordinates are in x's and y's, okay, on a regular trig graph. So, the cosine graph, all right, the cosine graph at right here, negative pi over 2 to pi over 2 goes like this, in this direction, from negative pi over 2 to positive pi over 2. And then from pi over 2, 0 back to this point over here. So it is closed. It is simple, but it's going the wrong direction. It is not oriented in a positive direction. Does everybody see that? This is regular trig graph going this way, then back here. That is a negative orientation. So what we have to do when we set up our integral is put negative signs in front of it. So we're going to put negative. We're still going to have a double integral. Now this is your P, this is going to be your Q. So you still take your derivatives just the same. You take the partial of Q with respect to x, which is 2x. Take the partial of P with respect to y, which is 2y. And we are going to integrate 2x minus 2y dA. Now, to set up my limits of integration, I'm just going to leave it in terms of x's and y's. This, my y values are going from 0 to the cosine of x, and my x values go from negative pi over 2 to positive pi over 2. So when I set up my integral, I put negative, and then I would put negative pi over 2 to positive pi over 2. I will put 0 to the cosine of x, 2x minus 2y. This is dy, and this is dx. And that would give you the value of that line integral, f dot dr. Because the region is closed, and we changed it and used Green's theorem. So let's see if we can get a problem here. Integral of 2x minus 2y. 2 cosine x. Oops. Okay, and when I put the negative in front of it, I'm going to get pi over 2, I believe. Is that what you got? Okay. All right, is there a question about Green's theorem and how to do these problems? All right, remember, if you're doing a line integral and you recognize that it is a closed, simple curve, and it's going the right direction, it is much easier to use Green's theorem. But if you cannot recognize that, then don't use Green's theorem. Just do your parametric equations of each of the lines, of each of the things, and add them together.
In what assignment is it going to want you to do one or the other, or is it going to say does?
These all say use Green's theorem. On this section, everyone says use Green's theorem. So they're all either positively oriented simple closed curves, or they're negatively oriented, which means you just stick a negative sign on it. Just the main thing you have to look at this WebAssign is just look at the orientation of the curve. Okay.